Uh, good good evening, all participants. I would like to invite Professor I. Sunita Garu to introduce today's session expert. Thank you, madam.
Thank you, sir. I'm audible, sir.
Yes, madam.
So, respected head of the department, N. Pushpalata, co-coordinator, and Dr. P. Harish, coordinator, and today's session speaker, Dr. Ramakrishna Sai Gorti, and all participants. Good evening to one and all. It's my immense pleasure to introduce today's speaker, Dr. Ramakrishna Sai Gorti Garu. He's an esteemed professor and the Dean of Academic Affairs at prestigious institute IIT Tirupati. He is a distinguished academic and researcher and has made remarkable contributions in the fields of computer vision, pattern recognition, machine learning, deep learning, and many other cutting edge domains. Sir holds the PhD degree from IIT Madras and MSc Engineering from Indian Institute of Science, Bangalore. His groundbreaking research has been featured in esteemed publications including IEEE, Elsewhere, Springer, etc. It's a privilege to have such an accomplished thought leader among us and look forward to gaining valuable insights from his wealth of knowledge and expertise. Sir, once again, on behalf of our institute and management, we are very happy to have you, sir. And all participants are really honored to have your session, sir. Thank you, sir. Over to sir.
Thank you, madam, for the introduction. I'm sharing the slides. Hope you are able to see the slides. Hope the slides are visible. So were you able to see the slides? Am I audible and slides are visible? Request one of you to unmute and tell whether the slides are visible. Yes, okay. Yeah, I am not able to see the chart because I am sharing in full screen. So request to verbally tell if you would like to interrupt me at any time. I am again sharing the slides. I hope the slides are visible. Okay, so I am assuming they're visible and going ahead. Okay, yeah, thank you. So of course you can interrupt me in between. The talk essentially is a kind of a fundamentals on artificial intelligence and machine learning. So what I will be doing, of course, I will not be discussing on the whole fundamentals of artificial intelligence and machine learning. In fact, AI is rooted with in the early stages of its like evolution. The what researchers thought AI is supposed to be and how AI should be has made several transformations during several past years, and what they anticipated at that time, that is completely a kind of a framework versus what is evolving is different. Okay, and given that I will not be bringing a kind of a initial approaches, especially the rule based approaches. What I will be discussing more in the discussion in this talk is fundamentals of image processing, one of the applied domain. Of course, not the core domain of AI, but applied domain of AI, especially that is more relevant to ECE and kind of signal processing students or faculty. And then fundamentals of machine learning, and how now both of them together enable us to perform some of the very automated tasks very efficiently. So that's the topic of the talk. So you can feel free to interrupt me in between or anytime. Uh, So before I start the discussion, this is IIT Tirupati administration building. And here are few of the labs in electrical engineering. Of course, you are welcome. Many of you are welcome to come. Of course, you may need prior permission and contact. Probably you can take from any of the faculty or students, and then request. Say if it is formally, if you would like to visit, you can make a request for visit, and then you can visit any of the labs. Of course, there are some equipment and resources available to use of public as well. And such things, in fact, you can use them on the nominal pay basis. So iSTEM is the portal through which you can make such feasibility of using the equipment that is there already at IIT Tirupati. And IIT Tirupati, as of course, I have not put the other images, has a very beautiful campus with several academic, residential, and as well as administration buildings, hostels, and so on. So, on the mountain backdrop, you are welcome to come and see. In electrical engineering, we do have BTech and MTech programs. BTech program, electrical engineering means it is ECE, electrical, and in fact, it also has the courses on machine learning, deep learning, computer vision, and so on. Just to have a overall blend of the applied and as well as core electrical. And we have MTech in signal processing and communication. Now we renamed it as signal processing, communication, and machine learning. Similarly, microelectronics and VLSI, there is another MTech, and then RF and microwave. 3 MTech programs running in the Department of Electrical Engineering. And we have programs like MS by research, wherein we take of just after BTech students for research. And like MTech, it is equivalent to an MTech program, but more research oriented. And we do have programs like PhD, where direct entry for PhD under some conditions from BTech itself, and or the MTech students can get into the PhD through selection process. We have 21 faculty now, and then we have enough staff, and many of the PhD students, now it crosses 40 or touches 40, and then MS students also is close to 15. The research goes in that in the areas of machine learning, medical imaging and computer vision, power and control, wireless communication, RF and microwave, and electronic devices, microelectronics, and so on. So we name our lab as VISA lab, Visual Information and Signal Analysis lab, wherein I belongs to the Department of Electrical Engineering, and this is the lab. We take all masters and BTech and PhD students. Of course, the areas include the signal and image processing to the current deep learning. So what I will be discussing in the talk is I will broadly give a brief. I assume that you have very minimal background on image processing and machine learning. I will be giving a kind of a brief background of these areas, and subsequently I will be discussing on some of the key methods of this area, and flashing some of the applications. So this is this lecture is only a pointers, gives you pointers, and it is no means complete, in the sense that you will not be able to do tomorrow without knowing any other things. Just with the lecture, some image processing application or machine learning application or any AI application. However, you will have pointers wherein you can get reading material, these steps to follow. If you want to be excel, if you want to excel in this area, or if you want to further do research in this area, and also some of the pointers on how exactly what are the skills required, and what are the methods that you should look more into, and so on. What applications can be tackled. So this is the talk perspective of the lecture. So the area of AI, when we consider, it's essentially artificial intelligence, as the name indicate. And what we want to impart intelligence for, it is for a machine or a computer. And sub areas under that are computer vision. And of course, image processing is a low level vision task. Like vision we have for humans, how do we impart the ability of not just vision, that is the ability to look, but also the ability to infer from what we look, like we do in our human vision. Okay, so in the similar manner, how do we do with the computer or with the machine? That's the objective of computer vision. And for that, what are the tools and techniques used? Nowadays, very well known tools and techniques used are neural networks and its counterparts or its developments, and what the applications we can do with that. So that's essentially the discussion. The problem comes for this automation or artificial intelligence or the ability to understand the scene from the computer is that the way human look and the way machine looks is completely different. That means what we see when we, in fact, we do not fully understand. And but we can understand that there are several objects, there are persons. Okay, that's in a context is happening, and so there are the several other, in fact, auxiliary information we have to infer from the scene that we see. Whereas for a computer, what it sees is just a matrix of elements, nothing else. 2D array of elements it sees. From that, what we want to impart is the ability like we have, in the sense that we would like to make it also to think, okay, and then tell whether it is correct or what class it belongs to, what object is it, where is it located, what is happening, is it moving or not moving, say what is the context, can I make a kind of a story out of it, all these things. So whatever the human vision has, with several auxiliary information, that we would like to have it for a computer also, with the set of elements or set of numbers that it see. That's the challenge. Okay, and that is not very easy, and it's in fact not at all easy. And given that, how do we make some of the algorithms to develop in that direction is a kind of the study under computer vision. So if we see this, for example, if you want to know that there is an object here, I need to know the boundary of the object. Okay, and then say that this is the only object is in this location. Or if I have 4 or 5 objects, I can say that one object is here, another object is here. So essentially the object boundaries will delineate, will separate the objects. So how do I know the boundaries, for example? Or if I assume that I have separated the objects. Now, I want to describe a cat versus a dog and then tell that this is a cat image, this is a dog image. How do I do? I need to have a description from the set of numbers I have. So those are called features or attributes. How do I get the set of attributes that describe a particular object of interest? That we have to do it from the image or array of matrices. So essentially, when we see flash in a scene with a camera sensor, what will happen is each of the camera will have CCD sensors, and it will have a 2D arrangement of sensors. Each sensor will look at a small region in space, and it averages the average intensity. It averages the intensity in that region and put a value there. And the value will usually range, if it is a 8-bit image, the value range from 0 to 255. Okay, so like that, it puts a value based on the average intensity each CCD sensor element looks. And there is a 2D array of CCD sensors, will put a 2D image. Like for example, if I have 1 megapixel camera, so 1000 cross 1000 array of CCD sensors or CMOS sensors we have, each of them will be looking at small regions and put a value there. Okay, so how do we, like that is what we call it as the image. And each value that it puts, we call it as pixel element or picture element or pixel. Okay, so from these we need to see the object boundaries, extract features or attributes of the objects, and we want to tell what the object is, where it is located, what is happening across the objects. Okay, all these aspects. See, how is it done? But the current, in fact, current development so far, okay, the key developments, if we see, there are only couple of things. If you understand thoroughly and well, you can understand how we are able to do it. one very important such thing is convolution or correlation. In fact, it should be very familiar to the like electronics or ECE engineers or ECE BTech or ECE students or faculty. The convolution is where do we use convolution, or where does the convolution stems from? If I want to find an output of a system for an arbitrary input, first what I do, I give an impulse. Okay, that means impulse means a sudden signal. Okay, which is momentarily exists at time t equal to 0 to a system, records its output, call it as impulse response. Okay, and h of n in terms of the notation people use most of the time. And then I take the original signal x of n, I do convolution with the original signal x of n and then h of n, or f and h, which is shown here in 2D, okay, and get the output. That I call as the output of the system. This convolution process, even though looks like very simple and in fact very primitive in signals and systems, is the key for all developments, most of the developments, even in a recent era of deep learning. Okay, what are we doing with this convolution? See, this convolution is also a kind of related to another term called correlation. What is correlation? Those who know from statistics or those who are from mathematics background can easily tell that correlation is essentially finds out the similarity between two vectors or two images or between two signals and so on. Correlation essentially identifies the correlation or the similarity between two different variables or vectors. Okay, and here in terms of two signals. So if they are similar, the correlation will be high. If they are not similar, correlation will be 0. Or if they are anti-similar, their correlation will be -1. Okay, something like that. And this correlation, or in fact, ideally speaking, normalized cross correlation, where we normalize it with its magnitude, is essentially is indication of how similar, okay, two different signals, images, etc. are, right? And this is same as convolution, except that convolution means you flip the kernel that you do for correlation and do correlation. That is convolution. Okay. So this convolution and correlation are key for extracting better attributes of the objects and for processing, reprocessing and enhancing the quality of signals or images or data, and also are key for matching templates, identifying the location of a word in a audio, identifying the location of a object in a scene or image. So for all these, the base is correlation and convolution. So if you properly understand the operations of correlation and convolution, in fact, the half of understanding, okay, of how exactly the recent methods are able to work is done. Okay, so here, for example, if you see, what we are trying to do is, say, for example, separate different objects. So to separate different objects, what I need to do is object boundaries. So to find out object boundaries, what are object boundaries? Where there is a sudden transition of the signal or intensities here in image. Wherever there are sudden transitions, we say they are, okay, object boundaries in image. See, where is the transition here? If you see, here is this positive and coming to the negative here. Okay, so there is a sudden transition. How do I know that? You make a correlation with a template that also looks like that, right? So you see this, for example, there is a sudden transition from -1 to 1. Okay, of course, -1 to 1 is a big transition. If we consider the whole range is -1 to 1 itself. Okay, so that means if the range that I can consider for this elements is -1 to 1, then it is one extreme to other extreme. It is going. Okay, that's what is seen here. See here, if I see, this highlights the vertical edges, wherein you can see that vertical edges, there is a sudden transition from -1 to 1 again, right? So, and if I do correlation means what? I put a kernel or a filter at this location. I do element-wise product. I make the value that is element-wise in the overlapping region with element-wise product at the center. Okay, so that is correlation. I do it at every location. Right? Hope this is clear. And that's how I get gradients. So these are essentially gradient finding gradients in x direction and or in horizontal direction and vertical directions. Once I get gradients, what we do, we apply kind of a, of course, overall magnitude of gradient root of gx square plus gy square. Okay, and then threshold it to get the gradient magnitudes. That threshold will give us edges. Okay, so this is essentially one of the primitive operation in image processing, but this essentially separates objects of interest. Okay, so it gives high level inference as well, right? And similarly, this also is useful for feature extraction. What are features here? Feature means what? Attributes. Attribute, object attribute, object boundaries indicate object attribute. So you can see here, for example, for person, the boundary you can see. Similarly, for a object, this is the boundary, right? Like that. So for feature extraction or for a kind of a processing, we do use correlation and convolution, right? The modern machine learning frameworks, what do? Is they do this correlation and convolution very effectively. That is only the difference. Otherwise, the current state-of-the-art methods does most of the times correlation and convolution. Okay, so you can see here visualization of the correlation and convolution, wherein you can see that this is the filter or the mask or the kernel. Okay, different names people call. And then this has weights. Okay, you have a image or the signal. You put this, say when I want to do perform correlation, you put it superimpose at the location, wherein at the center location where I want to do get the correlation result. And then g of x comma y now is equal to f into w f of x comma y into this 0, 0, w 0, 0. So which all these things, and you get the output, right? Element wise product in the overlapping region, and then summation of each of the product values will give you output. Okay. Now you can see that not just the processing is done through correlation and convolution, but many of the real processes happen through correlation and convolution. See, for example, if a car is moving, I have a static camera. During its exposure time, it sees not just a small region, since it is moving, it looks at a region 1, region 2, region 3, like that, several regions, put average of all these things at a given pixel. That's how a moving car looks smeared in a image that we take. Right? So what is happening here, as you can understand, that the correlation or convolution is happening with a filter that is averaging filter across x direction, and you are getting the result out of it. That means the blurred image that you see essentially comes from the original image, which is clean and without like blurring, convolved with a kind of a averaging kernel is what you see as all. So the real process itself is being done with correlation. Now here challenge is, how do I do inverse process of this correlation? See, if I have a signal, I have put through a system, right? I got an output, but somehow now I want the input signal back. What do? I design an inverse system, right? So inverse convolution or deconvolution, or figure out a convolution kernel or a filter that is inverse of the original filter. Then convolve with it. Then I get the original signal back, right? That means if I want to get f from g, I have to do convolution of g with h inverse, right? So that is what is designing the inverse filter or doing a kind of a inverse deconvolution. That is also needed for processing here, but the real operation itself, that means a car moving in front of a static camera or camera moving with the camera shake, is done while taking a picture. This gives convolved result, of the original scene with a particular averaging or whatever kernel, right? So the real processes are also real samples or images that we get are also already convolved or correlated with a kind of a degradation kernels. So now understanding this correlation and designing appropriate correlation kernels is essentially of great importance to extract better features, to extract better okay, enhancement, and so on. That's what is done in the, in fact, recent advancements like convolutional neural networks that I will be discussing in little later. Of course, computer vision is a mix of several fields, not just computer vision. Many of the fields now, if you really want to apply a practical problem, you can't confine yourself that I only will, work on signal processing or mathematics, okay, or only on physics, okay, on whatever area you are in, computer science. Okay, you have to be aware of the like the areas around to make any of the practical application. See now, the what I have discussed through pure correlation is essentially a kind of a processing task, wherein the input is an image, output is also an image. That is called image processing. In computer vision, the objective is slightly different. Input is image, of course, but the output is what? The inference. Say, for example, if I want to know how many number of razors are here, that is a computer vision task, not an image processing task. What are we doing here? We are essentially, we want to count the number of razors, but counting the number of razors is difficult because they are of different colors and so on. So what do we do now? We get the edges and then get a template of the razor head and then keep convolving the razor head with the different scales, orientations, and so on, and then try to see where it matches with respect to the image in the image. Wherever the razor head, okay, template means what? One razor head very clearly taken. Okay, this region is I can consider as template. Try to see with the different orientations, different scales, okay, where it matches in terms of correlation. As I mentioned, highest correlation score means that it is matched. Okay, it is 1. Very similar. Okay, if it is lowest, 0 correlation score, no correlation, no similarity. Okay, minus 1 means it is exactly anti, okay, matching kind of in okay. So computer vision has to deal with such task. Uh, mm, and this is another example of computer vision, wherein, see, the computer vision and image processing methods are developed in 2 different ways. One are dense methods, other are sparse methods or feature-based methods. Other is whole image-based methods. Feature-based methods means what? I want to know, assume that I have taken a big scene and I have taken a panorama, like I have taken several snapshots of the scene. I want to make the panorama of the scene. What do I do now? See, you see this image versus this, say for example, this image versus this image. Are there anything common between these two? You see that the human is common. Okay, and this is also common. So since I have taken the images like this, there are common things. What I want to do is stitch them. How do I stitch? The one way of stitching is, okay, exactly identify this region and same as this region and then try to align them. But other way of doing it is identify some of the key points or important or interest points. Okay, and then see that this point is exactly same as this point. This point is exactly same as this point. And then find out at least 10 points or 5 points here, 5 points here, and match them and align them. Okay, that's how is done in feature-based methods. And this is stitching. Of course, in the recent methods, it's done slightly differently. But here, the important point that I would like to make is if you want to understand a scene, it is not necessary that you should look at each pixel. Okay, you can look at some regions, they will give a better description of the scene. Okay, and they will give a better handle of the scene. Okay, in terms of how we can align, how we can make sense, okay, and so on. So the other very celebrated development in image processing, okay, what I will be discussing is I will be discussing some of the very well-known applications, okay, or the breakthroughs in image processing and computer vision. With that, I will be discussing on some of the theoretical aspects as well, okay, of understanding of algorithms. And then, of course, on the same direction, I will be doing with the machine learning. See, other celebrated work in image processing is essentially face detection. In all our cameras, you can see that, okay, they put a bounding box across the face. Okay, and how does they do in real time? Okay, the reason is they find out very simple templates that they match with the face to some extent. If you see this template, for example, okay, so this region is black and this region is bright. Okay, and that is the reason we would like to easily identify and say that, okay, in a face and say that it may be a face. Okay, another region you see here, this is also indicates that this can be a face. So essentially, when we want to make a detection or recognition of an object, we do not see the whole things. Okay, we see some reasonable attributes and we make a template or we make a kind of a kernel or filter of that sort. Okay, of exactly mimicking the features. Okay, that I would like to identify and match with, and with that we do correlation or convolution and get the like objects or whatever the important things identified. Okay, and the other important thing that I would like to mention, as I mentioned, the key components in making inference from images are two things. One thing is, of course, the kind of a processing of the image to make it better for extracting of the attributes. Second thing is the attributes. How do we make the better attributes or description of the image? And then third is matching. Okay. So here is example of what descriptors are good. Essentially, you can see angle of edges are one of the key descriptors. So these are also essentially, as you can indicate, you can uh, see the edges as we have seen before has direction. Okay, either vertical, horizontal, or inclined. Okay, has their direction and magnitude. So the direction is one which will help us to see, to understand what kind of shape the object has. Okay, so the strength of the edge along with its direction gives us a kind of sense of what object it is. Okay, so this is another breakthrough or important development in computer vision. Describing the objects or the images, okay, the objects in the images by histogram of orientation gradients. Of course, the histogram, you may be very well known that if I make the distribution of intensities, we call histogram for image. Distribution with different angles, how many number of edges are with this angle? That is histogram of orientation gradients. This is used for human non-human detection, and this is an example wherein we are doing stitching, face detection. Okay, and this is an example of using automated attendance system. Of course, different students have done different projects, wherein they try to get the detected faces and then also recognize them and give an attendance. Here is the example of other computer vision task. Okay, essentially visual tracking. What are we trying to do here? We are trying to do bacteria cells. Okay, we are trying to do track red blood cells, bacteria cells, and a kind of a clouds. And here is a kind of a pan, tilt, and zoom camera trying to follow a human. Okay, these are all like kind of a different applications of visual tracking. What are we trying to track here? So how are we able to track? Is essentially we characterize the object, okay, with a kind of a set of features. Okay, once we characterize the object with features or attributes, we try to see that in each frame the same object is identified, okay, matched, and with that we track the object. Okay, so once you understand some of the basic aspects of correlation and convolution and doing it in the learning frameworks, you will be able to do many of the computer vision tasks or any other AI task, in fact, very efficiently. Okay, so this is what the framework for any automation. If you want to do any automation, say for example, here we want to classify the fishes into two categories. Assume that there is a conveyor belt on which the fishes are coming. We want to put them into one of the two categories. Okay, say for example, there are Solomon and sea bass fishes. Okay, those who are Solomon, we want to put in one basket, and sea bass we want to put it in another basket. How do we do? We find out here you see that there are several fishes. We want to find out, separate each fish, for example, and then find out a object boundary, okay, and then align them, okay, and once we align them, we extract features of them, and put into one of the category. So for putting into one of the category after feature extraction, we do a kind of a GUI classification. What is what is done here is, instead of like for example studying a single sample, that means instead of understanding that this is a phase from a single patch or single phase image, we want to collect large number of phases, and we want to have a kind of a common attributes for the whole class. Based on that, we want to take a decision. Same is the case even for fishes. For the whole class of class 1 fishes and class 2 fishes, we say that class 1 fishes all will have these attributes, class 2 fishes all may have these attributes, extract such attributes, and based on the whole set of samples, we said that up to here you have class 1 samples, and up to here you may have class 2 samples, right? So like that. You can see that the feature extraction changes from the modality to modality. So for example, if it is audio, different set of different set of features are important to perform any automation task. If it is image, different set of features for image edges, for audio frequency details, for text something else, graphs and so on. Okay, but classification task will be almost similar. Okay, that's why in the conventional in the previous years, the signal processing area and electrical engineers used to study all these feature extraction methods, and the computer scientists used to study most of the classification methods. Okay, but nowadays there is no gap between them. In fact, the feature extraction is also done through learning, and for doing learning, you need better processing and feature extraction understanding. Okay. What now I will be doing is essentially giving some outline of the algorithmic developments, okay, for performing the automation task from the machine learning perspective to the deep learning, or the current era of like AI and deep learning. Okay, so the basic element or basic uh, uh, algorithmic component in each of these things is neuron. Okay, and the neural networks and convolutional neural network, recurrent neural networks, these are different models that are of course used in different flavors. So to understand them, you should understand about neuron, and you should understand about neural networks then. Okay, and then convolutional neural networks and so on. So what's a neuron? A biological neuron, if you see, each of the biological neuron, if you see, it has interconnections with several other neurons. Okay. So not just we have shown only one neuron here, but each of the neuron here may have interconnection with several other neurons. Okay. So, and each of the neurons that have connection will pass on some information. Okay. Through dendrites to synapses of this neuron. And then what will happen? The synapses of each of the synapses will get some inputs from several other neurons, and the synaptic inputs comes to the axon cell body, and more the net net weighted sum of the inputs, okay, comes as the aggregate information in the axon, and that is modulated and used for firing or not firing a neuron. Okay, so this is a simple mathematical model. If you consider, you have several attributes or several inputs that are coming for given for a neuron to take a call of firing or not firing. Firing or not firing can be, say, class 1 fish or class 2 fish. Okay, or face or not a face, a given image, cat or not a cat. Okay, something of that sort. Okay, so for that, what we do, for a given image, we extract attributes. Okay, x1 to xd, for example, are the attributes here. Each of the inputs to the synapses will not be taken with equal weight. Each of the synapses will be giving its own weight, right? So these are the weighted sum is taken, and that comes as the net output here, and that is modulated to get a fire or non-fire decision. Okay. So for example, here all are fired in this. Fire means all belongs to class 1. Non-fire means it is all belongs to class 2. Something like that. Okay, that means do an action, not do an action. Something of that sort. This is simple model of neuron. Now, what is the challenge here? Challenge here is what should I learn in this mm, what should I learn in this neuron? Essentially, we need to learn the synaptic weights. Okay, or we need to learn the weight, how much we give it to each of the input features or attributes. These weights initially are set random, and through learning process, we will finalize these weights such that all class 1 samples will be this side or and all class 2 samples will be that side. Okay, we learn in such a way. Okay, so now the question is, how do we learn? See, usually we formulate a cost function. Cost function meaning what? So for example, if a class 1 sample is classified into class 2, okay, because I have randomly initialized the weights, what will happen? A class 1 sample also, even if I give as input, it may be put as class 2 because of random weights. In such case, there will be an error. In that error, how do I minimize? Okay, usually for minimization, there are several techniques. One is the well-known technique that is widely used is, okay, in neural networks especially, is gradient descent. What is gradient descent? If you have function, if you want to reach out to the minima, if you are at this location, okay, you find out the slope of the function or slope of the, okay, cost function, error function, or slope of the curve. Okay, this itself becomes the curve in terms of a W variable here. Okay, and see, this is the slope which is in negative direction. You move in the positive direction. Move in the direction that is opposite to the slope of the function. How do I mathematically find the slope? Through derivative. Okay, find the derivative of the cost function. Okay, and then move in the opposite direction to by a small amount. And like that you do for each of the weights to update. Once you update, each of the weight is going slightly towards minima of the cost function, error function. What is the minima of this error function? It becomes 0. Why does it become 0? It becomes 0 because it's a square, right? So the minimum value of this will be 0, right? So like that. Now, there is a limitation for this neuron. What is the limitation of this neuron? The limitation of this neuron is, see, you will be able to tell a decision boundary which is linear only. If there are, say, for example, samples of class 1 here and class 2 here, or some of the samples are mixed, class 1 samples here, class 2 samples here, you will not be able to classify by a single neuron. This is a famous XOR problem, wherein the input features are given from x1, x2, and the output is essentially by XOR of x1, x2. Okay, and that how do we essentially solve? By a network of neurons. Okay, so we simulate a set of neurons. Each of them gives their own decision, and we non-linearly combine them to make a non-linear decision boundary. So essentially, this is a network of neurons. When we want to network the neurons, or when we want to combine several neurons, we need to understand how exactly we want to combine the neurons. Okay, so we or how exactly we want to organize several neurons together. The architecture that is widely used is called feed-forward neural network, wherein we have actually only, and also called multi-layer perceptron. It has a multi-layered structure, input, output, and hidden neurons. Okay, and each of the hidden neurons are connected to the input neurons, and each of the hidden neurons are connected to the output neurons. Okay, and the information goes only in forward direction, so it is called feed-forward neural network. Okay, and then the when I connect like this, there are several weights as you can see here, and then input is essentially x1 to xd is like the attributes. What do we mean by attributes? If I want to class fish classification, class 1, class 2, length of the fish, width of the fish, intensity of the fish, this can becomes the features, or face, non-face, classification. Okay, a patch having face will have some features. Okay, average color. Okay, the variance will be higher. Okay, and then nose location, nice location, or something like that. The patch not having face will have other attributes. Okay, such things can be here. Based on your problem, we will, or each of our problem, we will be designing of what attributes. These are the weights, and what we do, the weighted sum of all these things. Okay, will come to the any of the neuron. Okay, weighted sum of all its connections will come here. And that with modulation or nonlinearity comes as output. And weighted sum of all these connections comes here, and that comes as the output. When these are all randomly initialized, okay, the outputs will not be same as targeted output. If you want to classify a digit 8, okay, which is handwritten as correctly as 8 by machine, okay, initially if I randomly initialize, the output will not be fired here exactly for the 8th neuron. Instead, the output might be fired for the first neuron, something like that. Okay, so then there will be an error, and there will be an error at any of the outputs. So total error we want to kind of a capture and then use it to update each of the weight element such that error is minimized. Once it is minimized or very less, we will be able to see that this performs 8. Okay, when I give input as 8, the output 8 will be 5. Okay, something like that. Output of the 8th neuron will be 5. In sense, output of 8th neuron will be 1. Remaining all neurons will be 0. Okay, that's what is expected. As you can see here, this is an example of character recognition, right? Or digit recognition. So this and same is the principle in many of the other applications. Here you can see it is biometric recognition, essentially iris recognition. Here also we identify different attributes. Like for example, the eyeball, say size, and then the corona or whatever, the region width, and so on. Okay, different things. And object detection. Object recognition is also in similar lines. Object detection is slightly different. Detecting an object means what? We want to identify where it is. Okay. So that needs essentially a kind of a bounding box, exactly telling where it starts, okay, and then where it ends. Okay. So usually, if from a neuron, I can get a kind of a class label, I can also get a real value as the output. If I get the real value as the output, we call that problem as regression. If I get the class label as the output from a neuron or neural network, we call that as the classification. Okay. So when I want to do object detection, I will be posing it as a regression problem. Of course, in addition to the classification, because I want to know what object it is. At the same time, I want to know where it starts. Okay. So where it starts is the location values. That is the regression. This is essentially fingerprint recognition. These are few examples. And nowadays, one of the very important thing is essentially for most of the problems, we need data sets to be ready. For data set, that means the learning is not done with a single example. The learning is done with several examples. So if you want to do with several examples, how do we do? Essentially, we need to have acquire the data set first of all. Once we acquire the data set, then we can learn from several examples. That is what is conventionally done. Okay, so and there is one more change in the current recent methods compared to the earlier approaches. One key development, or in fact, it's a breakthrough you can consider, is that say here what you see is pre-processing, feature extraction, they are done differently, and classification is done differently. That means this is one algorithm, this is another algorithm. But nowadays algorithms does a kind of a pre-processing, feature extraction, and classification together. Okay, so what we are doing is the algorithm itself will figure out what essentially are good features, what are good pre-processing to be done, and how we do a kind of a classification or a high inference task. That is done in convolutional neural networks. So what the idea is, when we go in a layered wise structure, from initially we can have a very distributed information in terms of pixels. We can gather a kind of a slightly high level features or attributes in, and then another high level attributes. Finally, make a better inference. The way we extract features, as I mentioned before, is through convolution. Okay, the convolution or correlation is the key even in modern developments. As I mentioned, in convolutional neural network, the key in the block or the key operation is convolution, through which we extract better features, pre-processing, okay, and better features. Okay, so here what we are doing, each like if you have input image, the other important thing is we need not now limit to a kind of a like one-dimensional input. You can have two-dimensional input, you can have three-dimensional input, or any dimensional input. And you can design your convolution kernel also accordingly of that dimension. Okay, you can have a two-dimensional image, kernel also is two-dimension. Okay, and we are doing convolution and putting a value here output. And like that, if I do it at each location, I will be getting a kind of a feature or one set of attributes. If I do with different kernel, I have another set of attributes. Okay, I have with a different kernel another set of attributes. Like that, I will be having several set of attributes and in terms of feature maps. Okay, so these tag them and there are set of, say for example, I may be extracting corners, I may be extracting edges, I may be highlighting smooth regions and so on. These are all done at one layer itself. And of course, this is not the end of the story. So from that features, we want to do extract better features or a kind of assimilative features. How do we do is at the layer, next layers. Before doing that, what people do or what the another important building block of this convolutional neural network is essentially a kind of a sampling or pooling layer. What are we doing here? We are essentially grouping some of the information and putting a value output here. See, if you see A, okay, with bigger, say for example, A at, we will see that, okay, A seen at high resolution and at small resolution, both are visually similar. So there is no need of having those many details, and we can have a computationally efficient technique by grouping these similar information or efficient or important information. And that is done in terms of pooling or kind of a downsampling, and subsequently again done convolution to extract high level features. So essentially, as you can see, convolution operation is this. You can see a kernel moves on a kind of a image or a set of features and extracts a weighted sum and puts output as better features. Okay, so this is convolution. And here it is a convolution from 3D maps, that means several features maps, to a 2D. Okay, and another set of 2D feature maps, that means multiple layers. Okay, multiple feature maps to multiple feature maps. We are doing convolution or a kind of a convolution layer, constructing multiple feature maps to another set of multiple feature maps. This is explaining the pooling, wherein you see at this resolution or at this resolution really doesn't make sense, make difference for a computer. So it is good enough to pool the information and compactly represent so that we can reduce our operations. And also bring in a kind of a invariant. That means if I shift this A, it will be different from this A. But if I shift this A, but after pooling, both will look roughly same. If I see at very small resolution, the small shifts doesn't appear highlighted. Okay, so such is the like advantage of pooling. These two building blocks together, the convolutional neural networks, in fact, made a kind of a breakthrough. In fact, it's a much revolutionary breakthrough than all earlier methods. So the accuracies are the abilities to extract features, to perform directly the classification or inference at on the image data, video data is very high, and they were able to classify and they were able to perform other computer vision tasks much better. Here, what is the objective? The objective here is, see, you have different convolutional kernels. giving different feature maps. Okay. So how do I learn these kernels itself? I don't want to set a priori that I want to get only edges as features. I don't want to set a priori that corners are the features. What features will give me better classification or better inference? Such features I want to learn. How do I learn? Okay, I pose it as a kind of a optimization problem. So what do we do? You start with some random kernel, okay, random weights, okay, get one feature map, another random kernel, another feature map. Like that, these feature maps may not make any sense at the beginning. And pool that information also, even though they doesn't make sense. Okay, and get another set of kernels and then get other set of feature maps. Okay, like that you do it till the end and get a compact representation of the that means attributes of the image or the data that you have at the input. Once you get that, okay, you make 2D to 1D and get actually the final layer. Once you get that, next task is we want to say perform a classification. Then what do we do is we assume that it is a 10 class classification. Create 10 output neurons. Okay, and each of the output neuron is connected with all the features that we have extracted at the pre-final layer. It's like a feed-forward connection. And then if it is 2 that is digit that is as input, correct in like at the input, the output at the 2 should be high. But it will not happen if in a randomly initialized neural network or even convolutional neural network. In such case, what do we do? Find the error. Get the error. Okay, get the total error and use this error to adjust these weights and use the before kernels like we have seen, right? So this is the kernel W. All these weights are also adjusted with the error that we are getting. All these kernels are also, this is also W, got adjusted by gradient descent itself with the kernels. See, if we perform correlation, okay, in the forward process, we can see that surprisingly or interestingly, okay, the convolution operation gives us the weight update. That means, okay, the derivative of the weights with respect to the cos function, okay, is essentially obtained by correlation operation. If I perform forward process as convolution, okay, and then these are the typical feature maps. As you can see here, these typical feature maps will indicate what kind of features are we really extracting or the network extracting to make its decision. And you can see here with comparison with respect to the conventional neural networks. When you have a neural network with 3,500 neurons, okay, it's able to get 93% of accuracy in terms of classification for a digit classification dataset called MNIST. Okay, and the number of neurons that epochs that is trained is 1,000. Whereas a convolutional neural network with only 5 layers was able to do, okay, 96% accuracy with that means with here 93% and this is 96% with just a couple of like 5 layers. Okay, of course, if you train it properly, you can get 99.9% or 100% now with the networks. Then once people identified or once researchers identified a kind of a advantage in these frameworks, people started developing deep more and more of this kind of a learning based methods. See, there was a challenge called ImageNet challenge, wherein the data set has 1,000 classes and 1.5 million images. And the competition is launched. In fact, Professor Fifi Lee team from Stanford has acquired this data set from 2000 to 2010. And then, in fact, they have acquired 14 million images of cats, dogs, several cats, okay, several persons, and so on. Okay, different category, 1,000 categories. Okay, and with that, what they have data set is essentially is released for challenge, and the existing methods that means at that time in 2010 2011 you can see that they perform up to 75% okay, or with a 25% of error, right? But the deep learning methods or the convolutional neural network methods okay, which are started from 2012, okay, they could achieve an accuracy of 90, close to 90% or 85%. This has shown a kind of a great boost in terms of performance, and the limitation at that time was the computational resources, because to make these networks learn and train, you need to have parallel computing facilities, okay, the GPU cards. At that time, they have trained on two different machines and so on, finally combined and so on. But later years, the GPU facilities and then computing facilities have improved very greatly, considering their potential of development. Okay, and then we have now networks which are actually kind of 150 layers. Okay, and they do quite beating the human accuracy in terms of classification task. Okay, we mean by human accuracy, they annotated, several humans annotated anonymously, and they have overall, in the overall data set, around 5% of the errors. Okay, so the methods can get into almost on that data set of 1000 classes and 1.5 millions, get into almost 98% and maybe more now. So the methods evolved with, say, what I will be doing is I will be giving very high level picture of these, how they have evolved. They have evolved with kind of a uh, uh, two different important breakthroughs. One is essentially how effectively the information flow happens from input to the output and output to the input. Second thing is imitating the computer vision. Can we learn from multiple resolutions, not just from single resolution? Okay, so based on this, the developments have come. Okay, so I will not be going through the details, but essentially there are several data sets now then acquired for different tasks of computer vision, and different computer vision tasks are targeted. Like this is called detection. This is essentially called this is also object detection. Here single object, these are multiple objects, and here is segmentation, wherein you are trying to segment pixel level, okay, and try to give a label for each different objects. Okay, that means at each pixel you want to tell what class it belongs to, object class. Is it a cat, or is it a sky, or is it a green, or a build, like a whatever, okay, hill and so on. This is called segmentation, semantic segmentation, pixel level labeling. Okay, and then this is called object detection. This is also object detection, of course. Okay, XY location, as I mentioned, and then trying to give what class of object it is. Okay, and this is called instance segmentation. Even though there are three cats, all three cats should have been labeled differently. These are different computer vision tasks. Like I introduced visual tracking, all these things can be tackled with the current state of the art like convolutional neural networks. Okay. So now what I will be doing is I will conclude the discussion now. Also, we will take the question and answers, and we'll have a slide discussion. Of course, the set of slides I will be sharing with you. These set of slides have several references, okay, which you can go through to get much more details. You can also go through some of the like details, like how to get started, okay, in this area. So I'm sharing again to just show kind of details that you may be interested, and you can get benefited. So in fact, so those who want to get started in this area, so it's very important to understand some of the concepts like basic mathematics. You should be thorough. Okay, and then linear algebra and probability, little bit of coding, essentially with Python, and then subsequently probably with of course PyTorch and libraries of it. Okay, and then you should understand some of the video like neural networks and convolutional neural networks, and then you should take up some of the data sets like MNIST, digit classification data set, or character recognition data set, or image classification data sets. Okay, and then perform classification task first. It's a kind of common process for anyone who want to launch into this domain. Subsequently, you can understand about other deep learning method like computer vision techniques, and implement on them. Of course, Google Colab is the natural, like the resource that you have. okay, from any place. And then you have several other options. I will be skipping the details, but you can see several of these details in this slides, which will help you to get started in this domain. Once you get started, you will have actually several references that will point us, will help you to like understand any of the area that you are interested in, either for your research or for higher studies and so on. Okay, so and there are several allied areas wherein you can apply. This spans over audio, image, within image, remote sensing, medical imaging, finance applications, and so on. And then skill set required, I have already mentioned. Okay, several publications you should be aware of. Okay, and then some of the groups, very famous groups you should be aware of, where you can get good resources and as well as good updates of the publications and so on, and recent state of the art. And then you should, of course, you should get into yourself, wet yourself with mini projects. Then only you will be able to perform better, or you should be able to guide better. Okay, and papers with code is a common platforms, and you have some deep learning, you have some segmentation. These are other common platforms where you can get a good state of the art in each of these domains. And several companies are interested now in these. In fact, almost all companies look at these trends and want to adapt them in their company. So, of course, I will be sharing the slides, and you can go through them and write to me also in case if you need any further inputs. So now session is open for the questions and like small interaction. Yeah, you can. I can probably take another 10 minutes for questions. Yeah, please. My request is any of the organizer can verbally ask in case of somebody has typed in the Google chat some of the important questions. Or otherwise, if they have freedom, they can also quickly ask. Yeah. Yeah. Quickly looking at
Yes, sir.
yeah,
Sir, good evening,
website
sir.
research purpose already I have mentioned. Say which already I have mentioned. Of course, you can use them already. So easy data, what parameters? See, on specific aspects, some of them I'm not aware. In fact, in easy specifically, if you ask, I'm not very well aware. Uh, of course, but there are data sets like PhysioNet wherein you get a lot of data of medical imaging. Yeah, of course, video lectures are now also very well available by many of the experts, in fact, including me. You can see video lectures of mine in my faculty webpage, wherein you can see in teaching, under teaching. Similarly, IIT Hyderabad faculty, Professor Vineet Balasubramaniam has, and IIT Madras faculty, Mitesh Kapra has, and so on. Any other questions and doubts you can ask? Otherwise, we can conclude. Oh, missing data. Of course, nowadays several techniques are there for missing data. Usually, if it is in image, you can do kind of in painting at the beginning itself, or some of the methods directly take with the missing data and then they process. You can make the connections off at that locations. Okay, in terms of drop connects kind of thing. Or you can first impute the data and then do processing. Yeah. Any other questions? Oh, thank you all then. Oh,
Sir,
yeah.
sir, thank you, sir. Shall I conclude the session? Or participants, do you have any doubts regarding this session? Or we can conclude? Any participants? Yes, sir. I think so. No doubt, sir. They have posted in chat box already.
Yeah.
I would like to express my heartfelt thanks to Dr. Ramakrishna Sai Gorti, sir, for providing a comprehensive overview of image processing, perceptrons, neural networks, and convolution neural networks, and computer vision tasks and their applications. And also, you have provided the links for various data sets and papers and textbooks, sir, which will be very helpful for our faculty group for expanding their work or to learn the information, sir. Thank you for your insightful session, sir. Very thank you, sir.
Yeah. Thank you all. Bye.
I request all participants to stay in the line such that second session will be started soon. Good evening, sir.
Good evening, sir. Ayyappa, sir. Sir, you are not audible, sir, it seems to be.
Can you hear me now?
Yes, sir. Yeah. I would
Yes,
like
sir.
to invite Professor Airala Sunita Madam Garu to introduce today's session to expert, madam.
Thank you, sir. I'm audible, sir. Harish, sir.
Yes, madam.
So it's my great pleasure to introduce today's session speaker, Mr. Nutanapata Ayyappa, sir. He's a distinguished industrialist and accomplished professional. And sir has 20 plus years of experience in embedded in network industry, now presently working as senior principal engineer in Marvell Technology. Sir has demonstrated exceptional expertise and leadership in the industry. Throughout his impressive career, he has contributed significantly to renowned organizations, including Cisco, Wipro, Ericsson, Dell, Gigamon, Innovim, and presently with Marvell Technology. Sir has a remarkable journey in the tech world, which begins with the foundation he built upon earning his BTech degree from prestigious Sri Venkateswara University in 2006. Sir, we are privileged to host such an eminent personality and look forward to gaining valuable insights from his wealth of industry expertise. Thank you, sir. We are all honored to be here with you now. And over to you, sir.
Okay. Thank you for the intro. Thank you so much. Let me share my screen. Hello.
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 Yeah. Okay.
It's audible, sir.
Yeah. Um, can you see my screen?
Yes, sir. Screen is visible.
Okay. All right. Let me put it to the slideshow. Okay. Are you looking at the big screen or the small screen? I don't know. Hello.
Yes, please proceed, sir.
Okay. All right. Thank you for the intro. Today I'm going to discuss about the embedded networking in data center and AI applications. Myself, I am Ayyappa Nutalpati, I think the other Eddie mentioned, gave the intro about what and where I have been working. And so I've been working as a senior principal software engineer in Marvell Semiconductors in Santa Clara campus. So let's start. So this is about me. I know the intro has been done, but I just wanted to introduce myself. So that I did my bachelor's in electrical and electronics engineering in Tirupati, the Venkateswara University College of Engineering. I've been working in various companies in the last 20 years, but most of the time I've been working mostly on the networking industry. So I worked on various levels in the networking, close to the hardware, close to the application, close to embedded systems. Have worked in various domains inside the networking industry as such. And you can see the list of companies that have been working here. And I have a couple of patents in the similar domain. And you could see my family picture here. So I have 2 girls. And moving forward on discussing this topic, I have split mainly this discussion into 2 topics, 2 subsections, I would say. The first section is basically, it's not in full screen. One second. How about now? Can you see the full screen now?
Yeah, now full screen is sharing, sir. Thank you.
Cool. Thank you. So in this topic, we are going to discuss 2 subsections. The first section, we are going to discuss mainly on the embedded networking, on how it has been used or deployed in the current data centers. And in the next subsection, we are going to mainly discuss about the data center evolvement in the era of AI applications that have been recently we are looking at, right? So these are the 2 subsections that we will discuss today. So let's get into a deep dive of the first section. So this is a basic prerequisite that I'm going to talk about. Like we should have understanding on the network terminologies and the embedded concepts for all the slides that I have been discussing, going to discuss in this session today. But it's not a mandatory thing, but feel free to interrupt me if you are not able to get onto any terms or any understanding gap. Feel free to interrupt me so that I can give a quick glimpse on those terminology or the concept that we are going to discuss on particular slide, so that everybody is on the same page. So data center network. So basically, these data centers are like all over the world, and these are mainly used to develop large scale systems. Like they'll be in a centralized and controlled environment, which will be hosting various applications. Like we're talking about like anything like Google.com or Amazon.com or any hyperscalers that we see today, right? All of them host their applications or services in these data centers, right? And these data centers mainly comprise of 3 core components. The first component is basically the compute. So which means the data that are being fed to these data centers has to be processed, right? So that is the compute section of it, right? That compute section will take care of processing the data. And the second section is storage. And that section will mainly, the data will be stored. This could be storage arrays, or it could be multiple various of memory types that they can be using in the storage in this data center racks. And the third core component is the networking, so which connects this compute. It could be connecting to the storage, or it could be connecting to the outside world from this data center, or within the data center, across the racks or across the components. The key role that is played in the data center is the networking, right? And we're going to talk more mainly about the networking component of the data center today. So since we are getting deep dive into the data center network part of it, let's go over the high level requirements, what it needs, right? The high throughput, the high availability, and the wide scalability, the low latency, and robustness. So we're going to have a quick glimpse on each of these requirements in the subsequent slides now. Throughput. So in the networking world, the throughput is mainly measured in bits per second. So that's a common unit that to measure the data throughput on the networking connectivity. The more the throughput, which means that a system can execute more and more the faster the tasks, right? As long as the compute and storage can handle those operations, if the networking component can give enough throughput, then so that's the best that data center could handle. And these data center network speeds could range from gigabits per second to terabits per second. So there is no megabytes. It's like mostly gigabits or terabits, or possibly that petabytes is also coming in the upcoming IEEE standards now. But yeah, at the current deployments, you will see mostly in gigabits or terabits per second. And these data center storage and server components that are connected, or at least the connectivity onto the storage server, storage arrays, or the server racks, today you will see from ranging from 1 gigabits to 100 gigabits per second. But altogether, these storage arrays or the server racks, to get that connected, you need switches or routers, right? So these are basic network components that will connect all these storage arrays or server speeds. So the speeds on these switches and routers that connect these servers and storage arrays could have the port speeds ranging from 1 gig, 10 gig, 25 gig, 40 gig, all the way till 800 gig. And you have even the upcoming 1.6T. So this is each port. We are talking about the port speed on each port on the switch that is connected to these networking nodes. We call it a server or storage or whatever it could be, right? And each switch as such, right, that is connected on each of these racks could range their capacity from 1.6 Tbps to 1 or 2.4 Tbps, right? So that could have, each switch could have the ports ranging from all the speeds that we talked about in the previous slide. So if you look at this evolvement of how the port speeds and the switch speeds has been taking path, right? If you could see the first graph that's from a public source, where you would see that in the initial days, it has been less than 100 gig speed, and over a period of time, it's dying down, and then you are seeing 100 gig and 200 gig and 400 gig has been taking hold of this 100 gig speeds now, and we are jumping into 800 gig speeds and 1.6 Tbps as well from the port speed perspective as we move forward. And in the second graph, you are looking at how the switch speeds are getting evolved over a period of time, right? Like you are seeing in the current 2023 and 2024, you are people are moving from 12.8 to 51.2T, and then they have some evolvement of the 25.6T also is coming in upcoming phases for top of the rack switches, and then in the future they're targeting for 1 or 2.4 Tbps as well. So the right graph, you are mainly looking at the total switch speed, each switch or router that is connected in the data center, and on each switch there will be ports, right? So those networking ports is the left side graph that we are talking about. The next data center requirement we are talking is the high availability. So the goal of the high availability basically means it's data center applications needs continuous access, right? Whatever the services they are hosting and the access to the data on those data centers should be available all the time, right? Irrespective of any hardware failures or any disruptions, or it could be power issues or a link issue. It doesn't matter what failure a data center could have, but it could be even the failures could be on the compute itself or storage itself, right? It doesn't matter. End of the day, the high availability goal is to make sure that the access to those services is always available. So that's the pretty good, much high level goal of the high availability. So every node in this data center network, right, we talked about. So those usually have multiple paths for the connectivity to make sure that they have redundancy always in place, right? So they could have the connectivity either active or standby, which is basically means that the link will be active, and if there is a failure in the active path, then the standby path will take into picture. Or there could be scenarios where there will be active path, like each node will have a connectivity, and both the paths will be in active mode, and if one fails, then the 100% of the load will come to the alternate active path. So depending on the use case, each node could be using one of these options. And the network operating systems on the switches also provide this high availability, right? From the software also, they need to have an high availability. A switch or a router can go through a software upgrade, or a server can go through a software upgrade, or there could be a link failure, or a port can go down. So they need to make sure the software has enough infrastructure to handle these upgrades or failure management. And also the network protocols. So network protocols are basically the what do you call the at least in the Ethernet world, these are the standards that are defined that are used to communicate across these switching or router nodes, right? So there are multiple such protocols available in this Ethernet networking world, where you can get the HA availability, because when there are two nodes that are either running in active standby mode, or active mode, the nodes should communicate each other to know that they are in active mode or active standby mode, and whom they are partnering with, right? So to have that communication, there are certain network protocols available in the standards, right? So you could see here, some of them I have listed is that multi-chassis link aggregation protocol, which is used to aggregate the link speeds, right? Like you can have a 10 gig link aggregated with 10 ports, you'll get 100 gig speed, right? So this, and then when you are spanning across those port speeds on different chassis or different nodes, then you are achieving that link aggregation across multiple chassis, right? And then you have other protocol that is available, ECMP, where this is mainly used for the routing in the L3 routing world, where you wanted to distribute the router traffic across multiple paths. And we have another protocol called virtual router redundancy protocol, where a IP address, a node or a router are usually represented with IP address today, right? So you could have multiple nodes in a system, in a data center system, could act for the same IP address, so that one can act as an active, and the active goes down with the same IP address, the standby will come into picture. So that's the VRRP protocol. There are multiple such protocols that are available in the market today. I just listed a few of them, which are mainly used in the data centers to achieve this high availability. Okay, to have a quick glance on the high availability mesh network, you'll see here at each and every level, the nodes have multiple paths to the next level. So that makes sure that the connectivity always is in place. The next requirement we're talking about is the scalability. So in this the high demanding world, you need to have the flexibility to add the capacity as fast as possible. It could be adding servers, it could be adding storage, or it could be adding more network components to it. So you should have the flexibility to add them. You could add it on the horizontal way, which is basically you are adding more and more racks to it, or you are adding vertical way as well. Like you are adding multiple components into the same rack. If a particular rack is like, you could think of like one column in this right side picture that you are looking at, is like, you call it as one rack, right? That each rack in that each rack in the data center could comprise storage, compute, and you will call it something called like top of the rack switches, and that will provide the network connectivity to adjacent racks or to the outside world, right? And these racks are modularly designed, right? So where if you wanted to remove certain storage slots, or you want to remove certain compute slots, or you want to remove the networking switch as such, so it should be modular enough to replace as fast as possible if needed, right? And also virtualization is also playing a key role in data centers today, right? Where the service that you are trying to host need not be natively running on that particular compute system or the storage system, right? If you can run it on a virtualized way, like a Docker or a container or Kubernetes, so if you run those virtualized applications, then it is easy to port those applications from one system to the other system as and when needed. And the topology also plays a key role. We are going to discuss much about how these network topologies are constructed in the data center, and the interconnects. We talked about the port speeds already, right? And this is a key thing for the hyperscalers today. Low latency. So latency is basically needs the minimal time a data that should be on the wire, right? So it should be mainly used, the data should be either on the source or the destination. It should not be spending a lot of time on the wire, right? So that's the latency part of it. It should be as low as possible in the data center world, right? So that mainly depends on how you design the network, right? On what architecture do you want to deploy, and what is the use case that plays a key role today, right? And also this high speed connections play a key role on how you will try to make sure that it has low latency networks. And you would also need to run sub-second convergence routing protocols like BFD, or there are multiple such protocols that you could be running even on the hardware today to make sure that the latency is as minimal as possible. And there are multiple on-premise hardware-based neighboring protocols are also in place today to make sure that you detect the latency and then converge as soon as possible. But also the proximity placement, right? So you try to replicate the same data across multiple geographical locations so that the access to the data is as fast as possible. And that's also another part of the goal from the high availability. You're making sure that data is not lost on one place, right? If the data is replicated in multiple places, then you will be able to access at any point of time, even if one side goes down or the other side is always available. There are multiple such applications available in the market which needs this low latency in the market today. Like think about like live streaming or trading that needs the nanosecond level latency. And then you can think about even the online gaming. All those applications demand for low latency today. Robustness. So robustness is also like a key thing. Like when it comes to the physical connectivity from the networking world, it has to be fault tolerant enable, or it has to be robust enough that it could be withstand the outside environment. It could be under the sea, or it could be going under the ground. Wherever these cables are installed today to connect these interconnect data centers, it has to be robust enough that you will not have at any point of time any failures. So having said that, these are the key requirements that we have discussed from the data center deployment perspective. Getting a little deeper into the topologies or the architecture, how we design the data centers today, right? This is one of the architecture that been typically used, which is a multi-tier data center architecture, where you will see the southbound. So the southbound, what we call it as usually the lower part is called a southbound, and the upper part is called as the northbound. That's the common terminology that is used in the networking world. So if you see in the southbound, we have the servers, which are connected to the access layers, and the access layer is connected to the distribution layers, and the distribution layer is connected to the core layer. And the core layer is what is connected to the outside world today. So based on the layer, the switch, like all these three layers, the top three layers that we are talking here, basically are the switches or the routers that we're talking about now, right? So all these three layers will have different capacities, based on the layer that is being deployed on. It could be the top layer, the core layer switches could be the high speed 102.4T, or the distribution layer could be the next level speed, or the access layer will be the little lower speed switches that they will be deployed for. And the traffic that we are talking about, as I mentioned, it could be the north-south traffic, which is like basically the servers are trying to access the outside world, or it could be the traffic could be flowing between east-west, which is basically the server on the left-hand side could be accessing some data on the server on the right-hand side. Like that's called the east-west traffic. So these next 2 to 3 slides will be mainly talking about each layer that we discussed, right? The core layer is the very high speed packet switching backplane, which is basically used to handle all the flows going in and out of this data center today. So this core layer will be the high speed internet switch, and it provides connectivity to multiple aggregation modules and provides a resilient layer 3. So mostly the layer 3 is what router traffic is what the deployment you will see at the core layer. And you cannot have a single point of failure here. That's why you will see multiple core layer switches. And you might be running either OSPF, BGP, or EAGRP, which is basically used to load balance the traffic between these campus core or distribution layer switches using multiple hash algorithms. So these hash algorithms mainly utilize the packet parameters. So if you look at any networking packet today, you will have multiple fields, right? Like IP address or MAC address or TCP session information. So all those information can be used to compute any hash algorithm and determine multiple paths. If there are multiple paths, this hash algorithm will help you to identify which path should be taken for the northbound or the east-west traffic that we discussed. And the next layer switches that we use is the distribution layer switches, which is also called as the aggregation layer. It basically gathers the traffic from the access layer, which is on the southbound, and sends the traffic to the core network layer, which is on the northbound, and provides a single point of connection between these two layers. And this distribution layer is also used for the east-west traffic, which is basically the server-to-server traffic communication also happens through this distribution layer. And it can also use inbuilt services like firewall or any server load balancing techniques. All those things will be deployed on this distribution layer. So these distribution layers are deployed in pairs to make sure that we have the redundancy, which is one of the key data center network requirements that we discussed. Access layer. So this is the layer which is mainly in one of the pictures I mentioned of each rack, right? So on that each rack, there will be a switch that is placed on top of that rack, which is basically the access layer. This access layer has the actual connectivity directly to the servers, right? So there is a direct connection from that servers to this access layer. And sometimes it's possible this access layer switch connectivity are integrated within this server itself. The server itself the server rack box could host the server compute and storage. Also, it could host an integrated switch as well. So that's also possible based on the use case. And this access layer network infrastructure could consist of the modular switches. It could be either 1 RU or 2 RU, which is basically means one unit inside each rack is called RU. So depending on the capacity of that rack, you could be installing a 1 RU switch or a 2 RU switch. And these access layer switches can provide both layer 2 and layer 3 functionality to address a broadcast domain or administrative requirements that is needed for the server connectivity. So one of the other topologies that are mainly deployed in the data centers are the leaf-spine topology, which is the two-tier class network. So in this case, you will see the northbound layers, the north and southbound traffic will have 2 layers instead of 3 layers as compared to the previous architecture, where the servers are directly connected to the leaf, or we call it as the top of the rack. And this leaf will be directly connected to the multiple spines. And the spine will have the actual core layer 3 router traffic that is connected to the outside world today. These network operating systems, right, that is running on the switches today can have vendor-based switches, which will be running their own proprietary network operating system, which is not so. So the network operating system can be developed by each own vendor by their own proprietary OEMs or ODMs today. But having said that, over a period of time, there is a huge demand for the open source. So the Sonic is one of such open source technology that has been recently widely used in the market. So this Sonic is basically the software for the open networking in the cloud, which is a open source community where anybody can start contributing to the new features that they wanted to use in this network operating system, or they want to do any bug fixing, or they wanted to give any inputs on their new requirements or new deployments that they foresee. All those discussions happen in the open forum today, so people can contribute to this Sonic, and will be widely used by any white box, right? You could take a white box off the shelf today for a switch, and then deploy this Sonic operating system on those switches, and then you can start up and running today, right? So that's the whole goal of this Sonic, which is basically the faster technology evolution, because you are going to get the contributions from multiple vendors and also the operational burden. So this Sonic can be operated with unique CLI across the standards, right? Like if you have Sonic, if you have multiple vendor switches in the data center, then you need a different configuration management for each of these switches, right? And if you have one single Sonic open source operating system running across all the switches, then you will have easier simplified management, configuration management on those switches, which could be running outside the data center controller, like call it as a controller, where the controller can communicate with all these two-tier network or a three-tier data center network switches or routers will be configured remotely through this controller model, and Sonic does support that today. And this is open and a modular software, and today most of the vendors have been supporting this Sonic operating system already. Look at the Sonic architecture. This is the network operating system high level view. You will see most of the protocols that the data center needs, right? Like it's a BGP or OSPF, all those things runs in this container way, like the BGP container, or they have a TeamD container or LLDP container, DHCP. So all these applications are running in container model, so that if any of this container fails, it won't impact the network operating system in the data center on that particular switch, to make sure that the connectivity is always in place, right? And if you look at this, the way that architecture has been designed here, the northbound, you will see all the applications that are currently that will be running are accessible for the network administrator, which can be used for him to either configure something or fetch the current status of the switch or the router. So all those things are available from these containers using the user space, right? And if you go down to the southbound, there is a database, the Redis server, which is used for the configuration management DB, and that will be interacting with all other containers. And ultimately, it is used to program the actual hardware, right? Like the actual hardware has to be programmed with the forwarding information, where the particular packet has been received. If it received on this port, send it on this port, or if it is a broadcast packet, send it run to multiple ports. So all those information will be programmed using this network driver and ASIC driver today. So have given a reference to this Sonic as well. So that is available publicly today. So anyone could refer to this to understand better on the Sonic architecture and contribute more to that Sonic. So this concludes the first section of the data center in the with embedded networking. Before we move on to the next section, anybody has any questions? Okay. All right. So moving on to the second section, we are going to discuss more on how these data centers are getting evolved with AI applications are in place today, right? There is a huge demand of a huge new set of requirements that are coming in as we see new set of AI use cases are coming into picture. Like if you look at generic AI LLMs today, talk about Llama, Gemini, or ChatGPT. As these new LLMs are coming in place, the demand and the new set of requirements that are coming to the data center is altogether different from what we have in a traditional data center networking today. So we're going to discuss more about what are these new set of requirements that are needed for the AI applications. If you look at the traditional servers in the data center network today, if you look at any server, you have a CPUs, which is mainly used for compute the data, and these CPUs are connected to the NIC. So the NIC is basically going to provide the connectivity to the outside world, right? This is a basic servers that you will see in the traditional or classic data center network world. And these servers and each of these servers is what we just talked about, which could be connected to the front-end network, where it can have the access layer, distribution or aggregation layer, or the core layer to connect to the outside network. This is the traditional network that we talked about already. And these data centers will have connectivity across them with using the data center interconnect. These core layer switches in each of these data centers, which is deployed in two-tier class topology or a three-tier multi-tier or multi-tier data center architectures, will have a connectivity with the data center interconnect to the other data centers, so that you have the high availability, you have the redundancy in the data center. So those are connected with this data center interconnect today. And this is the pretty much the classic data center network at this point of time, right? And going forward with this AI servers, you have a new set of different hardware architecture, as well as new set of network requirements as well has come in place, right? And you will see here, compared to the previous picture, you will see the AI servers, you will have GPUs that are running behind the CPUs. Now the CPUs has taken a backseat on computing a little bit amount of less data, because GPUs are much faster, and these GPUs can handle 10x or 100x, maybe 1000x more than what CPUs can do today, which AI needs these GPUs to process that high amount of data. And these NICs are also slowly being replaced with these DPUs, which is basically called as the data path processing units. And this also is getting offloaded some of the tasks from the CPU on some of the security related network security related applications, which are running in the past with CPUs, has been offloaded to the DPUs. And some of the high compute applications has been offloaded to the GPUs, so that the CPUs are taking a backseat with respect to the AI applications today. So each such AI server, if you look at this each of the block that we have highlighting here, the CPU and GPU server, there are tens or thousands of those GPUs are deployed in a data center network, right? Which are connected to the outside world using the 2-tier or 3-tier class topology, which is basically the classic front-end network, right? The classic front-end network will have the access to the outside world, and these CPUs and GPUs will be fetching the data from the outside world using this classic front-end network. And as I mentioned, the scale of these GPUs are tens and thousands of each on each of these data center. And these GPUs needs a backend network. These GPUs needs a backend network as well, right? You'll see some orange connectivity where we call it as the GPU fabric, which is the scale-up network. We'll talk about more on what is that scale-up network is. And this connectivity is mainly provided through different network technology, not the basic Ethernet. Could be PCIe or other interface standards that is available today. Along with the GPU fabric connectivity, they also need network Ethernet connectivity across these GPUs, which is called the scale-out network. So that's basically an Ethernet. So, and the requirement for this backend network is altogether different compared to the classic front-end network. And you will see why and how we are going to use that for the backend network. The need for the backend network. As I mentioned, these AI servers running the AI models have been growing as fast as possible, that they have trillions of parameters that they cannot fit all those data in one GPU to be processed, right? So they has to spread across these all parameters to run the AI models across tens and thousands of GPUs. It has to be split so that to run the AI model. And many such instances of such AI model has to be trained in parallel within a data center across multiple racks or across data centers using the data center interconnect. And these models has to be synced periodically across. So make sure that the data has been trained and then processed and then synchronized across these AI servers. And you need thousands of such GPUs to train one generative AI model today. If you look at the stages in this model training, which is not relevant to the networking part of it, but this tells you why there is a push for a different backend network for the AI use cases. So if you look at these iterative stages on this model training, you'll see the computation phase where each GPU will be computing based on their own data or input. This data is being fetched for each GPU from the classic front-end network. And then you'll see the communication phase where each of these GPUs will try to communicate across within the rack or across the racks of the servers. And then you'll have a synchronization phase where there will be communication about this model, AI model processed data across the racks in the scale-out network. It's called as the synchronization phase. These stages will keep on happening iteratively because there should be a huge number of iterations to complete a training job, and it could run for months and months to generate an AI model today. So since this communication and synchronization stages should happen as fast as possible, because these GPUs are so expensive, we don't want those GPUs to sit idle as the data has been communicated or synchronized across the server racks, right? So the network time has to be minimized as much as possible. The data should not be sitting on the wire for a long time. Then if you make that, then there will be a very much huge underutilization of these expensive GPU resources. As much as possible, the data has to be in the GPU node to be processed than sitting on the wire to transmit from one GPU to other GPU, from one rack to the other rack or across the data centers. So the network performance plays a significant role for this job completion time. So basically the job completion time is is to generate an AI generative AI model determines by the job completion time today. And this GPU to GPU communication also requires very high bandwidth and very low latency. And the front-end networks that we were talking in the previous subsection, using that the existing infrastructure does not have sufficient resources, because the front-end networks are used to fetch the data for the existing use cases or applications. And there is a dedicated backend network needed for communicating across these GPUs in the backend network. In the backend network, you will see two level of networks. Again, one is the scale-up network. In the scale-up network, you will see the GPUs, at least tens or hundreds or thousands of the GPUs will be communicating to each other in the scale-up network. This could happen even within a rack. In a rack can have hundreds or thousands of GPUs today, and it can have multiple layers of switching happening today. And the connectivity between those GPUs, as I mentioned, it's going to use a different standards, which is, it could be an NVLink, it could be an InfiniBand, or it could be even a UA-Link. So UA-Link is a newer standard developed by what we call it as the UEC, the Ultra Ethernet Consortium. That's a new group that has been formed recently. So which is mainly focused on developing new standards for for addressing the AI requirements today. So that's the UA-Link, and as I mentioned, there will be a high volume of data that is getting exchanged in the scale-up network, and every such use case, AI use case, always needs high bandwidth and low latency today. And the second type of network that we need that is deployed is the scale-out network. This scale-out network will have hundreds of thousands of GPUs. In the scale-up network, you will see tens and thousands, and then hundreds of thousands of GPUs when it needs connectivity. Then it goes to the scale-out network. So this can span across one data center or more than one or more data centers, right? And the bandwidth that is needed for this scale-out network is 10 times more than the front-end classic front-end network that is already being deployed today. And the backend networks are also using the typical two-tier class topology to reduce the total cost, because the multi-tier costs more, and the data centers have been more and more adapting to the two-tier class network nowadays. So to reduce the cost, power, and the latency. And these AI use cases to get very low latency, they have been demanding for newer technologies like packet spraying and reordering, and all the stuff is also coming as a newer set of demands for this AI. Basically, that, as I mentioned, as much as possible, they need to push the data onto the wire, and it doesn't matter how many paths it's going to take. Let it be spread across all the links, and then as long as it's spending less time on the wire, and as soon as it reaches the final destination, it can be reordered again. So those kind of new technologies has been setting it on stone by this new group, this Ultra Ethernet Consortium. Is a new standard that has been still in works to address all these requirements. So this concludes the need for the dedicated backend network with scale up and scale out network for the AI use case. And if you look at the key takeaways out of this, basically the high computational demand. So the reason why is that the learning models we talked about, like the various learning models, the LLMs that we have today in the market, they push the limits of the traditional data center infrastructure. That's the reason why it has to go through a new specialized hardware, because all these AI workloads need a special hardware, both at the server world, where you have CPUs are getting replaced with GPUs, and in the networking world, they are getting the classic front-end networks are not getting used, so they need to use the backend networks with specialized hardware so that they can get a high bandwidth and low latency with the specialized hardware, and scalability, right, is also and flexibility is also highly important to deploy these large scale data centers. And power consumption is also been a bigger problem considering the new hardware and the high bandwidth, low latency. All those requirements are being addressed properly, but power consumption is becoming a challenging part of it, where it takes a lot of power to compute all this, right? So that is getting resolved with new cooling technologies. There has been so much cooling technology evolving that's happening with the data centers. So I'm hoping that those power consumption concerns and the heat that it generates will be resolved with this cooling technology that has been evolving in this data center today. So this concludes my session. If you guys have any other queries or questions, feel free to ask.
If any participants have queries, kindly ask. Sir, there is a question in chat box. Is there any method of used improving latency with respect to cooling air?
Cooling air. Yeah, there has been new technology like liquid cooling is one of the newer technologies that is being evolved in the recent times. I haven't covered about the cooling technology. I'm not part of that industry anymore. But yes, as that's a good question. But that's a good problem to solve as well. As I said, we need to engage and find better solutions on the cooling technology today on the data centers, because that has becoming a huge problem. Yeah.
There is another question. What is the purpose of VLANs in data center?
So VLANs is basically used for limiting the broadcast domain. Like when you have multiple servers are connected, like in a data center can have thousands of servers, right? And each set of servers can be deployed for certain use case, right? Let's say one service is basically Gmail, or one service could be Google Drive, right? So where those servers which are part of the Gmail could be classified under one VLAN, where you will have its own broadcast domain, where it can be used to communicate with each other. The application that is using Google Drive with another set of servers will be in a different VLAN. So it will help you to segment virtually to make sure that the communication between those within the use case or within that functionality will be helpful by segmentizing the network into multiple such VLANs today. So that's a typical use case, and these VLANs are used for basically the layer 2 switching world, right? So the layer 3 needs an IP address and routing and other stuff, and VLANs are used mainly for the layer 2 world, for the segmentizing the broadcast domain for each use case that it will be used. Even it is used even in the campus today, right? Like each department in colleges, right? You can talk about like each department can be used as a one VLAN, right? And the broadcast domain will be limited to that particular department. So that's the purpose of the VLAN in data center or campus switching today. don't know if there any other question. I see dedicated backend network be scaled to handle increased data processing unit. So there is a question: how can a dedicated backend network to be scaled to handle increased data processing requirements? As I mentioned, this dedicated backend network needs a specialized hardware on each and every stage of it, right? The servers are being upgraded, not just with CPUs. They're also having GPUs are in place today. So to handle more and more, to handle more compute, to handle the compute data, and even the network as such has been evolving with higher bandwidths, right? Like and the lower latency requirements. This UEC is a newer standard that is being coming in place to make sure you have less latency, which might need a newer hardware in the networking world as well. Like the switches and routers needs to be upgraded as well to handle these AI use cases. But yes, it is an evolving thing that's happening as the requirements keep coming for the AI applications. Possible factors for the reduced power consumption. Yes, I think the power consumption part, yes, is there any, so there was a question about any possible factors to reduce the power consumption. And if you look at the embedded world, the nanometers, right? The way the newer switches and routers are coming from evolving with the higher speeds, and also they are having the processing technologies are also going to from used to be like a 7 nanometer to the 5 nanometer to 3 nanometer. So that they're trying to reduce the power as much as possible. The way the power is calculated today is based on per port, right? How much per port the power is going to be consumed. As you try to evolve with the newer high-speed products, that the power consumption is trying to be optimized mainly by having a lower nanometer processing speed, lower nanometer processing technologies. At the same time, this cooling technologies is going to aid to reduce the power, because these switching units or routing units or server units is going to generate a lot of heat, which makes to increase more and more power to be consumed. So these cooling technologies are going to aid the help reduce the power as much as possible today. As I mentioned, there is a lot of cooling technologies are being complemented to this networking world today. So there are a lot of papers and a lot of industry level discussions are also happening for cooling technology. But that's one thing which is not related to my industry, but I see that it's not a lot happening on those areas as well. And, what measures can be taken to maximize the throughput in high demand scenarios? Yeah, so the high demand scenarios, I think we talked about the high availability is one of the requirement, right? So there are multiple technologies available for higher throughput. Speed is one thing which comes with the hardware, right? So once you have deployed a network switch or a router, and the speed and the capacity that it can provide is very much limited. What it can do is what it can do. You cannot increase the speed of that switch or router there, right? The only way you could scale is having different technologies to handle the ports on multiple switches, right? You can have link aggregation protocol is one thing where you will increase the speed throughput. You could have ECMP at the layer 3 level, which will help you to handle multi-path scenarios to make sure that you have enough bandwidth to cover all the traffic that is going outside the server or coming towards the server as well, right? And I mentioned about even the hash algorithms as well, right? So these hash algorithms play a key role because it calculates the entropy on each of these packets. We don't want to overload single link with all the traffic, right? So you need to compute with a better algorithms and the hashing technologies on these packets, so that it tries to load balance across multiple links or multiple paths in layer 2 or layer 3 networking world. That's pretty much I could see on the questions from the chat window. Anything else? All right. If not, yeah. Thank you for providing this opportunity. I would like to thank you, Dilip Garu and Pushpalata Garu for providing this opportunity.
So there is a last question.
Session.
What are the common bottlenecks encountered when using GPUs for AI workloads, and how can they be mitigated?
Okay, so the GPUs, the common bottlenecks, right? Today's bottleneck, as we see in the industry, the main bottleneck is network. So GPUs are evolved so much that it can process huge amount of data today. The only bottleneck that is coming in place is the network, right? The network has to communicate or synchronize this processed data across the GPUs has become the bottleneck today. So that's where these new standards, as I mentioned, UEC, are helping to address these bottlenecks to make sure that the data has been processed faster enough so that the job completion time for any generative AI model to finish this the process, to finish the data processing in a faster way, so that the GPUs won't sit idle. GPUs are fast enough to run all the data that has been presented to it. It's only the network that connects these GPUs needs a lot of improvements today. The cost, I see another question there. How can the cost of deploying and maintaining GPU powered AI servers be minimized? I think the question, if I understand it right, it's basically the scalability and flexibility, right? That's the main factor that drives the cost. So the hardware part of it, I know that it can evolve over a period of time to have a better handling of more and more GPUs getting hosted on a single server will reduce the cost. That's ultimately is going to possible. But at the same time, the main cost that is that is seen as a main bottleneck today for deploying these GPUs or even these switches is administrative part of it. The operating cost of it, operating cost for these GPUs or switches becoming a huge challenge today. So that's where people, the industry analysts, and then even the vendors across this networking and server world have been looking towards more on a unified way of controlling these GPUs and networks at the same time, like configuring them in a faster way as the use cases needs different set of configuration or different set of change in convergence timings. So all those things has to be done at a controlled manner. So that has becoming a huge challenge, and there has been a lot of involvement happening in those operational cost being the huge factor today that has to be addressed today. Yeah. So what types of AI applications benefit the most from GPU acceleration? In the data center, the AI applications that are getting benefited from the GPU acceleration is mainly the hyperscalers, LLM models, right? The Llama that is being generated by the Meta, Gemini from Google, or even ChatGPT from Microsoft Azure. So all those AI applications needs these GPU accelerations. It's mainly in the data center world perspective, these AI applications benefit a lot from this GPU acceleration and the backend network deployments that happens across these GPUs today.
Any other questions from the participants? Or shall we wind up the session? Yeah, sir, I think so. The questions have been asked already. No new questions, I think so. No one was posted in the chat box.
Okay.
So I think we can wind up the session. I would like to express my heartfelt thanks to Nodalpata Ayyappa sir for providing the embedded various concepts in the embedded networking. That is, it starts from an embedded networking in data center, various protocols, topologies at the data centers, data center interconnections, AI server with the GPUs, AI clusters, etc. Many insightful concepts we have dealt with today, sir. This will be very helpful for the faculty community for their research work, as well as to include these topics in their curriculum for the students. Thanks a lot, sir, for your session.
All right. Thank you. Thank you so much.
Thank you, sir. Ayyappa, sir, thank you.
Thank you. Thank you so much.
Ayyappa sir, thank you, sir.
Yeah. Thank you.